So tonight we have two goals here. So personally, the first goal is to talk about the first exam, and after we talk about the results of first exam, as well as a little bit discussion on the solutions to all the problems for first exam, we will cover another new topic about the numerical integration to analyze a single degree of freedom system so that we can get the numerical results for any arbitrary leveling. So that's a little bit ambitious objectives tonight, but let's see whether we can accomplish that. So firstly, as you can see, can online students see the share the screen on your side?
Yeah.
Oh, thank you. So as you can see on the screen, and that's the statistics of the first exam. We have 2 90s, 6 80s, 4 70s, and 1 60s. And we do not have any students failing this exam. That's very good news. The highest grade is 96. So yeah, I believe the 2 90s, they are pretty close. So we have 96 and 94 or something. Yeah, if I remember it well. And the average is 81.3. So it looks like the average is above the B level. And that's very good news. And another I would explain about the grading of their class. If you take a look at the points on your work, you may be a little bit confused about if you do assumption of your points for each program, you will see that the total points you get will be a little bit smaller than the grade given to you. And the reason is why I did some curving on the results here. And I used the most popular curving equation to give a grade. Some of you may be familiar with that, but so that's results of the first exam. So any questions about the statistics over here? Everybody's good. So now let's talk about the solution here. So in order to make it so let's talk about the solution to the problems here. So can everybody see the problems on the left side and the solution file on the right side? So now let's talk about the solution. So for the first one, the first one, we have several students did it pretty well to figure out the final solution for this problem. And we have some students who showed adequate steps to approach into the correct solution, but unfortunately, some of you failed to select the correct answer to this question. And some of you treated this as a mathematical problem. That's okay, but the goal of this problem is to make sure you can compare the mathematical equation with the problem we have already discussed about a lot recently. Right? So if you look at this equation, this is a very ordinary differential equation. So this is very similar to the equation of motion. So we compare equation of motion. We will say so what's the equation of motion? The equation of motion, we have the m times c times u plus p is equal to 0. And we have the y dot plus. So if you compare the equation of motion with the equation given to you, we can definitely see that and assume the m is equal to 1, c is equal to 2, and k is equal to 16. Does that make sense? And next step, since there are 4 curves for us to select, so it's better to write the y in function of the time. So we need to know the natural frequency. It's equal to a over n. This is the natural frequency. And we can also calculate the damping ratio. That's equal to a over times omega n. This is smaller than 1, much smaller than 1. But since theta is smaller than 1, this is an under damped system. So in this case, we should be able to. So we have A, B, C, D, and 4 curves. This is under damped free vibration, and this is under damped free vibration. So which curve is which curve illustrates the response of the system? Is it A, B, C, or D?
Should be.
So up to here should be A or B. Should be A or B. So C or D, that's not under-damped system. That's over-damped or critical damped system. Yes, Hunter?
I took all the same steps up to this point, but on my exam you wrote, should WD be calculated instead? Is that something that?
Correct. Correct. Up to here, we can say either A or B. But whether it's A or B, we need to do more calculations here. Because this is under-damped system, so the period of the system is to be calculated based on WD under W and omega and omega D. So we can say that omega D, this is a damped system, so the frequency should be omega D under the omega n. So that's equal to times omega n. And that's equal to so we can quickly get the solution for this one. This one. So based on this information, we can calculate the natural frequency here, natural period here. So the depth period should be 2 pi over omega d. So that is a period. That is period. So either A or B, A or B. So if we look at A, and the period of A is from 0 to somewhere, and we have 0 displacement. So period for A is between 1 and 2, But what's the period of B? The period for B is smaller than 1, right? So A the PD is between 1 and 2 seconds, while B, the TD is smaller than 1 second. So the correct answer should be A under the B. Does this make sense? So this is the first problem. So any questions regarding the solution to the first problem? So the students online, do you guys have any questions here? Okay. No any questions? Let's okay. Go to the second problem. And the second problem is a little bit tricky here. Second problem. The second problem. So we are given the natural frequency omega n and damping ratio for A. So the problem requires us to figure out the relationship between the natural frequency and the damping ratio of system B. So for A, the omega A is equal to the P over MA. The frequency, natural frequency of the system A to be equal to the stiffness of A over the mass of A, square root of that. So that's equal to. So what is the stiffness of system A? So we have two springs. So each of the spring has a stiffness, has a spring coefficient equal to K, and those two springs are parallel springs. So what is the stiffness for system A in this case? 2 times K, 2 times K. So this is 2 times K. And where the mass is. The mass is M, and we know that this is equal to omega n. Given to us. So similarly, we have the theta A. So the damping ratio for system A, that's equal to C over 2 times MP and omega A. And that's equal to. So so what is the damping coefficient for a system? We have two dampers, and the two dampers are parallel. So the they should be equal to 2 times C. 2 again, omega 8, omega 8. We can just go ahead to use omega n equal to C equal to C over times n times k. So this is that we have already calculated the relationship between the mass and damping and the spring coefficient with the damping ratio as well as the natural frequency. Does this make sense? So next step, we can calculate for B. For B, omega B should be equal to the AB over. So what is the list for system B? We have two sprays in series, so that should be A over 2 over MB is equal to A over. So for the equation above, we know so this is equal to 1 over square root of where the square root A over M should be equal to omega n over square root of 2. So this is omega over 2. Does this make sense? So the relation between square root K over M and omega n is based on the relation given above. Right? Should be able to. So that we should be able to tell that relationship between omega B and omega n. So omega B is half of omega. So that's the. So in that case, we should. So A and C should be eliminated from the right answers. So either B, D, or C. B, D, or E. B, D, or E. Here, in order to answer the second part, we need to find the damping ratio for case B. So that should be the same thing here. This is a top. Let's see. This should be equal to this is equal to half of the damping ratio of system A. So up to here, you can tell the correct answer is which one? So none of the above. Right? The correct answer is because the damping ratio of system B is also half of that of the system A. System. So this is the second problem. Actually, this problem. So actually, all the three first three problems are accepted from the structural dynamics exam from Brown University. So, yeah.
So I basically got that problem wrong at 2 universities at the same time. Here and Brown University.
Yeah.
Awesome.
So yeah, if some of you did all the three problems correct, then that means your skills are comparable to the graduates from Brown University. Congratulations. But if you found it a little bit challenging, that's okay. That's okay. So, any questions for the second problem over here? Yes.
Why do we need A? Why we needed to solve the A portion?
You mean why do we need to?
You know how you have for B and for A? Why do we need to solve for A?
Okay, so the reason why is because so the frequency and the damping ratio for A is given to us, right? But but we would like to know the relationship between the damping coefficients as well as the strain constant to the with the given parameters there. It's only in that way we can compare the natural frequency between A and B or and the damping ratio there. So we have to represent. We have to present the natural frequency as well as the damping ratio in terms of the fundamental properties of the system, so that we can do more detailed comparison with you. And that's the main reason here. So without that information, how can we compare so for example, if we solve the omega B in terms of K and N, how can we compare the omega B with omega A? Omega A, right? So, yeah, so since the A and B, so all the mass, strain coefficients or the damping coefficients, they are comparable with better written we write the natural frequency as well as the damping ratio in terms of them, so that we can compare. So that's the second problem. Any other questions?
Yes, Professor.
Yes.
I have a question. Omega B, Like, um, why did you multiply by omega n over square root of 2? I don't get that part of it.
So you mean the second line of that derivative?
Yes, yes.
So the second line over here, so we have already derived the omega b in terms of the k and n here, correct? So we would like to compare omega b with omega n, and so that here we convert the square root, we represent the k over n square root with omega n, with omega n. So in this case, we can feel the relationship between omega b and omega n here.
Okay. But the question never really asked us to get a relationship. So my thinking was just square root of k over m is omega n. And then so that would just give us with omega n over square root of 2. And the only one with that in the answer is A. So
So up to here, if we have already expressed omega b over here, so how do you express omega n in terms of k and n?
that wasn't my thinking. I was just it didn't really ask for a relationship, so I just thought I could just calculate what omega b was without
Okay.
getting what omega a would be.
Oh, okay, I got what you mean. So you thought that the omega n should be equal to square root of k over m, correct?
Omega n over square root of 2.
Like half an hour. Is it in here? Thank you. What the
Yes, omega n is equal to square root of k over m. That's a general equation, but when you use that equation, you have to be careful. What is k? Right? K, that's the overall stiffness of this system. For example, for system A, the k should be, when you use omega n equal to square root of k over n, you should use k equal to 2 times k. Right? So that's why when we use the equation to calculate the natural frequency of system A, omega A, that should be in terms of square root of Ka over Ma, in order to avoid the confusion there. So that here, the stiffness of the system A should be 2 times K, while the mass of the system should be equal to M, not the 2 times M, just M, because we have only one mass. So the mass equal to M over here. So does that answer your question, Mikhail, or?
Yeah, I guess so.
Okay. Yes, yes, that's, so whenever we use that omega n equal to square root of k over m, we have to be careful, have to be cautious about what value should we use for k, right? Okay, so this is the second problem. The third one is. So problem 3, we are a system with a spring damper with the mass under a harmonic force. So, and we are asked about the amplitude of the vibration of the mass. So actually, the from the textbook or from our notes, to the response factor, so that's between the dynamic, so the amplitude of the dynamic load, the dynamic displacement over the static displacement should be equal to 1 over 1 minus beta square plus 3 times theta square. Right. Yeah, and we discussed that in class too. In the class. So for a steady state, or the steady state response of the system, so the ratio between the maximum dynamic displacement or the amplitude of the dynamic response over the static response should be equal to 1 over square root of 1 minus beta square plus that. So what is the beta here? Actually, the beta is equal to omega over omega n. Omega is the frequency of the force, the frequency of the force. So that means in this case, our case, what is the beta value in this case? So we are given the omega is equal to omega n. Means that in this case, it is equal to 1. So that the R should be equal to so that we should be able to so that's the amplitude of the dynamic displacement should be equal to R times the static response. So that's equal to R times static should be equal to the amplitude of the force over the rate constant. It's equal to where the beta here is equal to 1. So that's equal to beta. So beta is already equal to 1, so we do not have to consider beta over the theta. That's equal to 2 c over in this case, we should be able to get that. So this is the final answer. So should be B, actually B. A little bit derivation over here. Derivation. In order to answer that question, I will make you know about the response factor between the amplitude of the dynamic response and the static response. Yeah, we have one student, he or she explained that by guess, he or she selected B. Fantastic. Just by one guess, that's great. 10 points. Very good. Yeah, so that's the nature of multiple choice problems. 25% chance to get it correct, even by yes. So any other questions regarding the third problem here? Okay. So if no any questions, let's talk about the fourth one. Number 4, I think number 4 is modified based on your homework problem.
Air condition.
Air conditioner, yeah, very similar.
And I think in class it was a washing machine.
Yeah, but anyway, you say problem 4 is very similar to your homework problem. So I only revised the damping ratio as well as the frequency of the force. If you have already, so if you did check the homework solutions that I shared to you, you should be able to solve this problem correctly. And I'm nothing fancy here. So I would say for problem 4, please refer to your homework solutions. And I have also shared the exam 1 solutions on the OneNote file, and you should be able to have access to them. So please refer to the homework solutions for this problem. Really, pretty much the same as the homework. So this is problem 4. Any questions regarding problem 4? Even said that it's very close to the homework problem. Yeah, so firstly, you need to calculate the lateral frequency of the 2 beam. And then you calculate the frequency of the force. So based on that, you should be able to use the response factor. So that we use this in problem 3. So the R that's equal to 1 over square root 1 minus beta squared. So where the beta is equal to omega over omega n. If you calculate the value for beta, you should be able to calculate the R value and then the steady state deflection amplitude should be R times and the force amplitude over the K of the spring on the surface of the beam So while the amplitude of the acceleration should be equal to omega squared times omega 0 equal to just as long as you have this omega, that's the frequency of the force. This problem, no issues. And I believe the majority of the class did pretty well in this problem, pretty well. So the major issue that has already seen for the entire class is problem 5. We look at the problem 5 here. So problem 5, that's actually that's the application problem for a very common case you see in your everyday life. The hammer hit at the head of the nail, and we would like to know the maximum force acting exerted on the nail, as well as the time, the contact between the hammer and the nail. So before we solve this problem, actually, if you look at the model of this problem, so this problem has already shown you the model of this problem. So on the left side, that's the nail with the stiffness can be calculated as EA over L. And if you use a hammer with the initial velocity hit the head of the nail, and this system can be simulated with a spring and a mass system, so where the spring constant is the stiffness of the nail, and the mass is the mass of the hammer, So before you solve this problem, you need to ask yourself, what type of the problem is? Because so far we have already discussed the free vibration of a system, as well as the forced vibration of this system. So is this a free vibration or forced vibration? Should be free. If it's a forced vibration, what is the time function of the force?
An impact.
An impact. But can you draw can you plot the force versus the time?
Like an instantaneous.
It's infinitesimally small,
Mhm.
which we went over. I remember because he could spell infinitesimally and I was impressed. It was,
Okay, yes, some of you may assume it's a forced vibration. Some of you may take it as a free vibration. I would say both of the treatment should be okay to solve this problem. So actually, and if you remember, when you treat the forced vibration of the system under the definitely small impulse of there, actually, and the impact is more impulse. Forced vibration is very similar to a free vibration. Because when you hit the head of the hammer, actually, you just induced a initial velocity to the head of the nail, to the head of the, or to the hammer, So in this case, let's see whether we can solve this as a free vibration. Usually it is. We treat it as a free vibration case. If it's a free vibration, what is the solution of a free vibration system here? So without any damping, right? So no damping here. The response should be equal to U0 times So let's see the response function of the vibration system of the. So here we need to answer what is the initial displacement of this system. So when the hammer hits the rail, so does the rail has any initial deformation? So does the mill have any initial deformation? No, because the rail is there, so the initial displacement is equal to zero. So, but the initial velocity is given to us. The initial velocity of the mass is 5 meters per second. So actually, we can quickly solve this problem. So that we just need to calculate the natural frequency of the system. So that means we need to calculate the k value. That's equal to BA over L. To the E, it's this is the k value. Yeah, I think if all of you get the correct number for the stiffness, that's good. And then we have the mass is already given to us, so we should be able to calculate all of that. It's equal to this is the natural frequency, so that we should be able to calculate the UT. Is the response of the rail. Are there any questions after here? Okay. So what does this mean? This tells us the response of the layout, right? Actually. And if we so we have the hammer, hammer. So the hammer with the initial velocity equal to 5 meters per second. And the hammer goes to the left, and the hammer will reach the maximum displacement here. So this is the maximum displacement here. And the hammer will go back to its initial stage. So actually, we can draw the it's a sine curve. So that is the response of the nail. So when you will have the maximum contact force between the nail and the hammer, so that's where we have the maximum displacement. So that means the maximum force will be equal to K and the maximum displacement. That's equal to what is K here? And that is the maximum force. So here, that's the maximum displacement where you will have the maximum force, because that's where the spring has the maximum deformation. So this is equal to so any questions up to here? The maximum force between the hammer and the nail, and where we have the maximum deformation for the nail. But what is the duration of the time? The contact between the hammer and the nail? So the time should be, so this is the delta T. So initially, there is no deformation for the nail, and with time going, the deformation of the nail increases until it reaches the maximum, and then the deformation decreases to zero. And then after that, there is no contact between the hammer and the nail. So actually, the delta T here, that's the half of the period. So this is the delta T. It'll be half of the area. So that's equal to pi over omega n. The contacted path is very small, very small. Let's see for the point. 0.009 seconds. I don't think most of our words can record this time. So does this make sense? So that's how we can use apply the theory of structural dynamics to solve some practical problem. Online students, do you have any questions up to here? Okay, so if no any questions, let's talk about the last problem. So actually, the last problem, so right before the week before the exam, we discussed the response of the system under an arbitrary force. But actually, this is an arbitrary force because this is not harmonic excitation. When we talk about harmonic excitation, the duration of the excitation should be forever, should be infinite. But here, the duration of the force is limited to 0.2 seconds, 0.2 seconds. So that's different from the harmonic excitation here. So in order to solve this problem, we need to do the convolution integration, convolution integration over here. So we impose the response of the system is equal to, we do a, yeah, so if you look at your nodes before the week before the exam. So for any arbitrary node, the response of the system should be equal to, we do integration from 0 to t, not to t. So the steady state for an undamped system should be equal to 0 to t, where we have the p power and h minus r. So where the unit h theta is equal to 1 over n omega n and sine omega n e minus tau theta. So if we would like to know the response under an arbitrary force, the response of the system can be expressed in terms of the convolution integral, such as like this. Right? So for this problem, we just need to express what is the theta and what is the omega n in our case. So this and also for impulse node, there are two phases. So phase one, that's the forced vibration. Phase two, when the impulse is removed, that's phase two, the system will do a free vibration. Free vibration. So this is phase one. And the phase two. Phase two, the UT equal to the free vibration. We have the U, where we have this is the 15. So actually, in order to calculate the maximum deformation displacement, we need to find out the maximum displacement for phase one, but we want for phase two, so that we can find the maximum. I can find the maximum here. So in this case, that means that we anyway for phase one and phase two, both cases are associated with omega n. We need to calculate omega n. Omega n is pretty easy. We have the k over am. It's and that's that we should be able to calculate the omega n in this case. In the hand. So for phase one, we can just go ahead do the integration of the UT. And we can move down. So what is the function of the impulse in terms of and power and power?
Time.
So that should be $56 times sine 2 pi over 2. Omega And actually, we can substitute everything here. And in terms of 50 outside, that's side. So the remaining task is to do the integration of this system. Here. So in order to do integration there, you have to use the reference that I gave to you. I gave to you, so that you can write the displacement in terms of t, under the, so the tau will be canceled out because after we do the integration from 0 to t, from 0 to t. So after that, we should be able, if we express the ut or the function of time, we should be able to find the maximum displacement now, right? We can plot the displacement as a function of the time. We can find the maximum. So this is the first one, and second, similarly, we can do that for the phase two. We after we express the ut in terms of t, we can find the displacement at the time equal to 0.2 seconds, as well as we can find the velocity when the time equal to 0.2 seconds, so that we can write the response in terms of time for phase two, and we can find the maximum response for phase two. So the overall maximum amplitude should be the larger of the phase one and the phase two. So that's the, actually I have already posted the solutions to the file somewhere. Yeah, to the, there should be in the shared file of the OneNote file, OneNote over here. So please refer to the solutions for the remaining steps for this question. We yes.
Where is your OneNote file?
It's shared through emails to everybody. Yeah, so it should be shared. So let's check whether. So let's have a short break, and after that we will talk about the so this one. Yeah, so this note file should be shared to everybody. So Mikhail, your email is also listed in listed here. So you should be able to check your email to find out that the shared OneNote file. So the OneNote file is CE543 2022. So please let me know whether you can find it. If not, I'm going to send you a share link so that you can access it. Is that clear?
Yeah, I'm looking for it right now.
Okay, great. So yeah, please take a short break. We will resume the class at 8:55. So then we will talk about the numerical method, other than the evolution and integration. That's sometimes is kind of challenging. Okay, thank you. Talk to you later.
Professor Yang, I've been kind of thinking about like what you showed us for the project before we went on break. It has been haunting me.
Oh, okay.
Are we going to talk about that tonight?
Wait, is there a project?
Okay, yes, yes, actually, some of you, emailed me about the project. So, yes,
Other people are.
yeah, besides Elizabeth, talk about in class. Yes, I was assigned a project. It's, take a look at the project. So probably I'm just gonna extend the due date for the project because, yeah, it's almost the end of March. So, yeah, I will extend that to middle of April so that we will have adequate time. Because tonight is the first time we talk about the numerical integration over here. So actually, students online, are you guys back? Or, okay.
Yeah.
Okay. So I have already assigned a project on the Blackboard. Some of you have already started. Actually, that's fantastic.
Really?
Yes. Yeah. So this project is about the production of a response spectral. So actually, you are given an earthquake ground motion record such as shown here. So this is an earthquake load. Can everybody see the Excel file that on the screen? Actually, I believe students in classroom should be able to see it. But the students online, are you able to see the earthquake record on your screen?
Yeah, we can see it.
Okay, so this is an earthquake record, and so this is downloaded from the PER website, the Pacific Earthquake Engineering Research Center, is located in University of California, Berkeley. And I visited the center. It's located in a very small building. And I was very surprised in this very famous institution in earthquake engineering research, but located in a very small building. But anyway, this is a typical earthquake record that you can record from a device called accelerometer, mounted at the base of a building or any other types of structures. So this measures the acceleration of the ground during earthquake. So the x-axis, actually, that's the time. That's the time. So what's the duration of the earthquake? If we look at so maybe the number is too small. Here. Change that to. So what's the duration of this earthquake? So it's about 28 or something, or smaller than 30 seconds, smaller than 30 seconds. And so x-axis is the time, and the y-axis that's the acceleration. And so what's the unit for the acceleration? Actually, the acceleration is expressed as the ratio to the gravitational acceleration. That's g. G. So, for example, what's the maximum acceleration recorded over here? That's 0.4 g. 0.4 g. So, so when you input this acceleration record as a force, so actually you need to multiply the number by the g value, right? You can use the g either in the metric units or in the imperial units. Anyway, so you should multiply that so that you can get the exact acceleration number other than the ratio to the gravitational acceleration. This is a earthquake. So if you are giving an earthquake like this, if you want to do the convolution, the integration, it's impossible. It's impossible because in this case, and only feasible, it's only feasible for us to use the numerical integration. So any questions regarding the earthquake report over here? About the X and Y axis? Yeah, okay. If no any questions, let's go back to the. So you are required to write a program in MATLAB. If some of you are familiar with MATLAB or Excel, you should be able to do that in Excel too. To generate its pseudo acceleration response spectral for different damping ratios ranging from 1% to 20%. 1%, 2%, 5%, 10%, and 20%. And you are required to use central difference method or numeric integration method to calculate that response.
Either one.
And either one. So actually, next time we will talk about what is response spectral, and as well as about the central difference method and numeric method over here. So basically, the requirements. So firstly, you need to select a system with a given. So you assign the natural period for the single degree of free system there, ranging from 0.2 seconds to 50 seconds. So for example, you can select a set of 100 numbers ranging from 0.02 seconds to 50 seconds. And based on that, you should be able to use the numerical method to produce the response of the system in terms of acceleration. So that you can find out the maximum acceleration for each system with each system, and you plot the maximum acceleration versus the natural frequency of the system, so that you can get the response spectrum. So response spectrum is a very important concept. Because if some of you have already done some seismic design, when you do seismic design, the seismic load is specified as a design response spectrum, so that you can tell how much force you need to apply to the framing system of your building or the old bridge, so that you can calculate the maximum force or bending moments in your columns, braces. So that's the goal of this project. So this time we will talk about the numerical method called central difference method. Next time we will talk about the response spectral, so that you should be prepared for this project. So I will extend the due date of this project to the middle of the April. And after this project, probably we will have another project about using structural software to analyze a bridge or a building structure under an earthquake, so that you can get the maximum bending moment, axial force, as well as shear forces, so that you can do your design based on those analysis results there. So that's the plan for the project. As I mentioned in the syllabus, we have 2 projects, 2 exams. So you are done with one. For exam 1, you have another exam and 2 more projects there.
Don't they ask the next exam?
It's the
What?
final exam.
No, he says there's 3 exams.
Two.
Okay, because I was about to say, when's this other exam? Okay, so there's 4 big things.
Yes, 2 exams and 2 projects.
I had a moment, a cardiac moment, but it's over.
Okay, yeah, so we will not have a final exam, second exam scheduled before the final, so that you will be a little bit less stressful for the final. You don't need to worry about the final for this class. You only need to worry about the project. So the project 2 will be due the final week or before the due date. The last day of the class of this semester. So any questions regarding the project? Any other questions?
So due date will be April 15 for this one.
Yes, April, what is April? So when we talk about the due date, so the due date for this one, probably, yeah, 15 or 19 or 19. I will extend that to the middle of April anyway, for this project. Yes. I will talk about this project after we are done with the discussion of this response spectral for earthquakes. So don't worry about that. And I will also show you some examples of students from previous years. So that's the plan for this project, and I believe you will have a lot of fun using MATLAB or Excel to do some practical data analysis. A lot of very extensive data analysis there, and yeah, that's very important for nowadays engineers. So this is project 1, and this so that's why numerical integration is very important for you to be successful in this project. So tonight we will talk about the goal of tonight is we need to know how to solve equation of motion using central difference method. The first thing I'd like to introduce you to the numerical integration. So what is numerical integration? So when we talk about numerical, we talk about using computers to do calculations instead of hand calculations. So we have already learned that for a structure, we have, if we have a excitation, for the structure. So the goal of the structural dynamics is to figure out the response of the structure with any arbitrary input in terms of excitation. So we would like to know what is the response. We would like to know what is the response here. So for free vibration, that's pretty easy. if we have a single degree of phase system there. So free vibration, we should be able to have something. This is a free vibration, so it's a decay and sine of cosine wave, sine of cosine wave. That's easy, right? That's easy. And so for harmonic, harmonics, we also we should be able to find out the response of the system. We have the transient response as well as the steady state response. The steady state response is also a sine or cosine wave, sine or cosine wave. That's very straightforward. And for impulse node, so for some impulse node with a regular shape, such as rectangular, ramp, sine, or cosine impulse, or a step load, the response would be able, we should also be able to also the response would be two phases. Phase one, that's positive vibration. Phase two, that's free vibration. And that's what we discussed before tonight. But for arbitrary node, for any type of load, the solution would be we have to use Duhamon's integral so that the response can be figure out. Duhamon's integral, we have already talked about that. So if we have and that's ut, that's equal to e tau, that's ht minus tau. This is the Duhamon's integration around the h over tau is equal to this is the Duhamon's integral that we can use to find out any response for any node. Sounds it's very straightforward theoretically, but we have already all of you have already seen how challenging it can be if you wanted to use Duhamon's integral to find out the response of the system. Even you are given a sine wave impulse, right? So how much time it will take for us to do the Duhamon's integral? So in that case, nowadays we have the computer, so we need to figure out we can use the help of we can instead of doing the hand calculation on the Duhamon's integration, we can develop some numerical integration. To find out the response, instead of using hand calculations. So any questions up to here? So we have talked about different node cases. when the load is equal to 0, load is harmonic, the load is impulse or any load, theoretically, and we should be able to use the integration to find out any response. But in reality, there are some limitations of the Johannes integral. Some limitations here. So the first limitation is we have to assume linear system. And because the convolutional integration is based on the superposition of linear system. If it's non-linear, we cannot use the Johannes integral. Secondly, closed form solution not always possible. For example, if you have an earthquake, how can you express the p-power for an earthquake? If you have an earthquake, what will happen? And then it's also not generalized, Yeah, because if you have only one dynamic load, for each dynamic load, you have to use an integral. If each dynamic load is different, you have to use multiple integral. That is very time consuming. So those are the limitations of Johannes method. So now let's talk about one of the most popular numerical methods is called the central difference method. Actually, a lot of structural software is equipped with the central difference method. So when we talk about the numerical method, firstly, let's review the relationship between displacement, velocity, and acceleration. So if we know the displacement, how can we get the velocity? If the displacement of the system is given to you, derivative or derivative. So we do a derivative for time, so that we can get the velocity. So actually, the velocity is the derivative of the displacement to time. So if we have the velocity, how can we get the acceleration?
Second derivative.
Yeah, we do the derivative on velocity. Actually, the acceleration is the second derivative of the displacement. So sometimes we also call the velocity is the slope of the variation of displacement, while the acceleration, that's the curvature. So for example, if we have a for example, if we have the displacement as a function of time, and we are so at time ti, we know the displacement is ui, and then time t I minus 1, we have the so at the different, for example, we have 3 different times in sequence. The sequential time, the ti minus 1, ti, and the ti plus 1. And we assume the time step is equal to a constant time step. So that's equal to delta t, where the delta t is called the time step. And here, actually, we can approximate since we know the velocity of the so the velocity at time ti can be approximately equal to, if we use the slope from t I minus 1 to t I plus 1 to approximate the velocity. So that's why this method is called central difference method, because theoretically the velocity is derivative, but here we use difference. We use difference between t I minus 1 and t I minus plus 1 to approximate the velocity. Yes.
That's over 2 delta t.
Yes, that's over 2 over delta t, because the time from the first to the second, that's 2 times delta t. So that's the initiation of this method. And any questions up here? So initially, theoretically, the velocity should be the derivative of displacement, but you cannot have the computer to do derivative for you. You can only have the computer to do difference for you. So we have to use difference to approximate the derivative. Does that make sense? Any questions? Okay. So similarly, we can express the velocity in terms of central difference. We just use the same graph. And similarly, we can use the slope. And so we have a slope here. This is called the theta I minus 1. And we have a slope here. It's called the theta I. That's theta I. So similarly, we can express the acceleration in terms of the slope on the displacement, because the slope is actually the slope is the velocity, and the velocity. So that's equal to theta. So theoretically, the acceleration at time I should be the second derivative of the displacement, but here we can also use the difference between the slopes to express the acceleration. So that the acceleration can be expressed as the displacement 3 different times over the square of the time step here. So any questions up to here? So yes, so actually the core of this method is to express the velocity and the acceleration in terms of time step and the displacement at different times. So that's based on these two approximation. We should be able to solve the equation of motion. At the time yeah. So we have the we have the mass times the acceleration at time I, c times the velocity at time I, plus stiffness times the displacement at time I equal to the force at time I. And then we remember the acceleration and then the displacement and the velocity can be expressed as the time step and the displacement. So that we can have and we can reorganize this problem. We write we combine all the coefficients for the displacement u, right, plus 1. So that's easy, right? We just reorganize the problem and the equation so that we can have a different term, different form. So as you can see here, so for a given system and for a given time step, the factor for the ui plus 1, this is known to us. This is known to us, right? Typically, when you have the computer to work, you need to tell the computer what is delta t. Have the computer to work. So this is known to us because the structure mass 20, and we know that. And on the right side, the pi, that is the force at time I, that's known to us. As long as we know, for example, for an earthquake, we can tell at time ti what is the acceleration for that. So this is known, and this is known, and this is known. So now this problem has already been converted to a problem is if we know the time at I and I plus 1, I minus 1, we should be able to solve. If we know the response of the system at the 2 earlier times, we should be able to solve the displacement at later time, right? So that means we can have the computer to gradually solve the problem for any given time, But there are some details for the computer to initialize the computation before it can give us some solutions here. So we will, but the procedure is based on this equation, is based on the equation over here. So next time we will talk about more details, the central difference method, how we can use that to solve some problems. And we will walk through an example using Excel to see how powerful this method can be. I think that is 9:30 only. Our class ends at 10. Okay, we still have about 30 minutes. Okay, we will finish the central difference method. Sorry about that. So the class ends at 9:30. Was okay, guys. Yeah, please. Okay, so so if we look at this equation, we can tell that in order to solve the displacement at any given time, ti plus 1, we need to know the displacement at the earlier times, at the 2 earlier times. Right? So that means we need to know the initial condition of the system. So for example, the initial velocity and the initial displacement, if we know that, we should be able to have the computer to sequentially do all the calculations. So now let's see what should we do over here. Any questions before we move forward? So nothing fancy here, it's just some mathematical tricks. I would say central difference method is the mathematic tricks. So now let's see what will happen if we want to solve it. So that means that we need to know the initial. We need to choose the initial conditions. So for example, the initial velocity of the system is equal to u1 minus u minus 1 over u. It's delta t. Right? And Imagine equal to. So here it is, the strange thing here is that we can tell the U1 is a displacement time T1, but what is time T minus 1? So U minus 1 actually does not make any physical meaning here, but we should be able to solve for U minus 1. So we solve for U minus 1. So we have U minus 1. And so based on these two equations, we should be able to solve for U minus 1, and that's equal to U 0 minus T.
Is that a subscript -1?
Yes. Yeah, so U minus 1 does not have any physical meaning, but it just there's a mathematical number here, but we can solve for that based on the central difference equation because we know the velocity and the acceleration can be expressed, right? In those two terms, so that we can know the U minus 1 can be expressed as the initial displacement minus the delta t times initial velocity plus delta t square over 2 times the initial acceleration. Does this make sense? So now we can have the U minus 1, U0 as the initial condition. To find the U1 and to find the U1. So as long as we have the U minus 1 and U0, we should be able to find the U1. Excuse me. Yeah, because U1 can be expressed as the U minus 1, the U0, the U0. And we should be able to express the U1 in terms of U minus 1 and U0 here. And this method is stable conditionally. Conditionally stable when the delta t over natural frequency is 1 over pi. So mathematically, this method is stable under one condition where you have the time step delta t smaller than 1 over pi times natural frequency of the system. That means that the delta t has to be selected as small as possible, as small as possible.
Professor,
Yes,
what's
Yes.
in the denominator? 1 over what? Is that a TI?
1 over pi. Sorry, 1
1
over,
over pi?
yes.
Thank you.
What happened here? 1 over pi.
Kicking us off.
Over pi.
Greater.
So now let's look at an example to see how we can solve a problem. So that example is from your textbook. And we have an example. So we have the force. So the excitation is the impulse. So the duration is 0.6 seconds. Just put it there. 1 second, and the maximum force is 100 kips. So if we have a impulse node applied to a single degree freedom system here. This is a PP. So we have the K that's equal to and equal to 10%. And then omega n. And then C.
That's 6.283.
Yes. So this is knowing the dynamic properties such as the stiffness, damping, ratio, and the natural frequency. We should be able to use the tensor difference method to calculate the response of the system, such as we can calculate the displacement using the procedure that I presented here. So initially, we just use the initial displacement, velocity, and the acceleration. All of them equal to 0. So now let's see what will happen. So any questions regarding the problem statement here? Very straightforward here, knowing the dynamic properties, knowing the force. So what will be the response? What will be the response?
Is maps given?
Yes, mass will be given to you. Just the natural frequency is given to you, the mass is given to you. Right? Okay, so we should be able to do this, an Excel spreadsheet. So, so here, so firstly, if you wanted to, so the online students, can you guys see the Excel file on your screen now?
Yeah, we can see it.
Okay. So, firstly, we need to define a delta t. So the delta t can be expressed as so the largest delta t we can use, remember, is when the system is stable, we have to make sure the delta t is smaller than Tn over pi, Tn over pi. So that means so what delta t you can use? So for example, here I use the 0.1 second, 0.1 second. You may use a little bit larger delta t over here, but then not larger than a Tn over pi, a Tn over pi, the lateral frequency over pi. But how about you use a very small delta t, for example, 0.001 seconds? What will happen if you use a very small delta t over here? If you use a very small delta t over here, will your calculation be unstable?
Yes. Thing over pi.
And if your delta t is very small, your calculation will be still very stable. The smaller the delta t, actually the stabler of your system. But the issue with the much smaller delta t is the smaller the delta t, the longer the computer will spend to finalize the calculation. And or you will have a very large data on your computer. So typically, when you solve this type of problem, we just choose a reasonable large delta t other than a very small delta t. So for example, in this case, I use 0.1. So if we use a 0.1, so that means we can actually produce the time. So if the time is the time step is delta t, actually we start from zero, and so time is equal to 0. So the next time is 0.1. So everything is based on delta t. And now we should be able to express the force Ti at different times. I would say it's better to use Ti here. So this is the Ti. So at time Ti, we have the different force. So the force should be able to be expressed as sine wave. So if we plot the sine wave should be able to the whole. A second. So this is a sine wave here. So this is a sine wave here. So we have already approximate the sine wave with the time step equal to 0.1 second. Right? the time 0.6, the force is zero. That's very important. This is not a harmonic sufficiency sign with impulse force. So this is the initiation of the problem. We know the force is like this, right? And then the next step is we need to calculate the displacement ui minus 1, ui minus 1. So the ui minus 1 is calculated based on the initial displacement, velocity, as well as the acceleration. Remember this is u minus 1 should be equal to the initial force minus the delta t times the velocity plus delta t. So if we know the initial numbers, we can just input the initial numbers over here. So with that given, we can gradually input the equations. For example, those are initial ones, and this is the velocity at the time 0.1, and so the displacement at time 1, the u minus 1 should be equal to the displacement at the time 0. And so this is I make the ui1 at time 0.1 should be equal to the time equal to 0. Does this make sense? Or make it reasonable. Just put this as yi number. This is equal to 1. This is equal to 0. So at time 0, all of them is equal to 0. That's the initial condition. The velocity, displacement, and acceleration, all of them equal to 0. And time one, the ui1 should be I minus 1 should be u0. So this one should be equal to that one. And does this make sense? And the ui, and now ui can be expressed as since we have an equation for u1, so u1 should be equal to u. This is the u1. U1 should be equal to u minus 1 plus the velocity at time 0 times 2 times delta t over here, so that we can write the displacement, the velocity, as well as the acceleration for the time 1 and time 1. So we use the same procedure, go down for each different time I, for different time I number and the ti number, so that we can get all the displacement and acceleration as well as the velocity, so we can solve all of them at the same time. So after that, we can plot result here, as you can see here. So this is the result of the central difference. Actually, I'm gonna not show this one. So the red one, that's a theoretic solution for a impulse of that before 1 second. And the black, that blue one, that's the numerical method. So you, as you can see here, they are very close. They're very close. So, and I'm gonna to share this Excel file to all of you so that you can study and see how the equations of the central differentiation method input in the Excel file so that you can use it to solve for any practical solutions. Actually, you can also change the delta t here. So, for example, you change that to 0.05, probably you will have a better solution close to the theoretical one. And as you can see here, there are some arrows. There are some small arrows here, but if you use smaller delta t, I would assume, I would expect to see some smaller arrows, smaller there. Yeah. So please try and do this. I'm gonna to assign this as a homework to. So I'll ask you to select the different time step to compare the results. So that's about the central difference method. It's a mathematical method to solve vector dynamics problems. So that's this method. And the next time we will talk about another method called numeric integration method. So they are, because why we talk about those two methods, because a lot of structural software, they use, some of them use the central difference method, some of them use the numeric method, and some of them comes with both of them. So then there's two methods. They have some benefits and drawbacks here. As you dig into more into the finite element analysis there, you will see and quite a difference here. And yes, I think that's all for tonight. So I'm gonna share this file to all of you and to have you practice this more after class. I think that's all for tonight. Any questions, please let me know. Thank you.